In this video we're going to see that every metrizable space is normal. The proof for this theorem is extremely straightforward. Because we are in a metrizable space, we are in a metric space, let's call it X with a metric T. We want to prove that this space is normal, so we have to take two closed and disjoint sets and prove that our space can differentiate between them. So let A and B be closed and disjoint. Let's draw the situation so that we can picture things a bit. This is our set A, and this is our set B. Now for each element I grab A, in A, I can always find a ball with center in A and radius epsilon so that it doesn't intersect B. I can do this for each element in A. And I can also do the same for all the elements in B. Let's write this down. For each A in A, we will call epsilon A some number greater than 0. It will be the radius such that the ball with center in the element A and radius epsilon A intersection B is the empty set. And we can do the same for all the elements B in B, such that now the ball with center in B and radius epsilon B intersection A is the empty set. But we could, when doing this, have situations like this one, where one of the balls in A intersects one of the balls in B. If I take the union of all these balls, then I will have coverings of A and B, but those two will not be disjoint, so I cannot get normality from that. I have to somehow make everything smaller. I could do it like we did in our previous video, in which we proved that regular and second countable implied normal. In that video we removed all these intersections one by one, but now we have more information about our space. Our space now is metric, so we have a sense of distance, and we can use that to our advantage and then take coverings that are a bit smaller. So I created all these sets, but now what I can do is just take the same balls with center in A, but instead of radius epsilon A, take it divided by 2. So if I index this in every A in A, this set is obviously a covering of A. And the same happens with B. The family of balls with center in each element of B and radius epsilon B over 2 is a covering of B. Well, and then we can just call their union U and B. So because these two sets are indexed in A and in B, then we obviously have that A is a subset of U, that B is a subset of B. But how does reducing the radius help? I mean, what tells me that this intersection is empty? Well, let's prove it. For this, we will take an element in the intersection. If set is in the intersection of U with B, that means that it will be in the intersection of one of these two balls for some elements A and B, in A and in B. So set is an element in the ball with center in A and radius epsilon A over 2. Intersection, the ball with center in B and radius epsilon B over 2. So let's calculate the distance between A and B. Because this is a metric, we can use the triangle inequality passing through set. So the distance between A and B will be less than or equal to the distance between A and set plus the distance between set and B. Now, set is an element in this ball, so this first distance is smaller than epsilon a over 2, and the other distance is smaller than epsilon b over 2. Now epsilon a and epsilon b are two real numbers, so we have two options. If epsilon a is smaller than epsilon b, or equal, the same would be if they're equal, then the distance between a and b will be less than, and here I can make epsilon a over 2 smaller than epsilon b over 2, and so I would get epsilon b, because I would have epsilon b over 2 plus epsilon b over 2, that's epsilon b, and this implies that a is an element in the ball with center in b and radius epsilon b. But these balls, we said we took the radius epsilon b so that the intersection with a would be empty. So this would be a contradiction to that. And the same would happen if epsilon b was less than or equal to epsilon a. In this case, the distance between a and b will be smaller than, and I would have epsilon a over 2 plus epsilon a over 2. That's epsilon a, and implies that b is an element in the ball with center in a and radius epsilon a. And again, this is a contradiction for the radius a that we took. And so this element set cannot exist, and we have that the intersection of u and b is empty. And so our space X is normal, which is what we wanted to prove.